The technical data presented in this film have been derived from preliminary reports. Therefore, any conclusions and recommendations drawn herein are tentative, since completion of evaluation for the final report is still underway. Redwing was a 17-shot operation, the most ambitious ever conducted at the Eniwetok Proving Ground. 4 were fired on Ivan, an airdrop, 2 tower shots, and a ground surface burst. In the Sally Pearl Ruby complex, 4 others were fired, all tower shots. There were 2 barge shots in the lagoon off Flora, and 1 was fired in a large tank of water on Irene. The Eniwetok shots ranged in yield from less than 1 kiloton up to 1.9 megatons. At Bikini, there were 6 firings during Redwing. The Cherokee airdrop off the island of Charlie, a surface shot, 3 barge shots off Dog, and a shallow water barge shot on the Charlie Dog Reef. Yields ranged from 380 kilotons to about 5 megatons. It was around these devices, all basically developmental in character with the exception of Cherokee, that the military effects effort was centered. There were 8 weapons effects programs consisting of 47 projects that were carried out by 18 different government agencies and laboratories. The Cherokee shot was included in the series to study basic military effects and fallout from a high-yield airburst over land. It also provided the first opportunity for the Air Force to test techniques for the delivery of a megaton weapon. The drop aircraft was a B-52. Height of burst was to be 5,000 feet, and 0 point was on the island of Charlie at Bikini Atoll. Blast studies in free air were concerned primarily with measurements of a high-yield airburst to document propagation of the blast wave through a non-homogeneous atmosphere. One technique used to obtain this data was to fire smoke rockets behind the 0 point to form a smoke grid, and then to photograph the shock propagation against this grid. A means of obtaining measurements of free air peak overpressures versus time vertically above a megaton yield airburst utilized an array of 12 parachute-borne telemetering blast pressure canisters dropped from a B-36. At shock arrival time, the canisters were to be in this position, ranging in altitude from 14,000 to 39,000 feet above the burst. The Cherokee weapon was detonated on 21 May 1956 with a yield of 3.8 megatons and a height of burst of 4,320 feet. This was the intended 0 point for Cherokee. This was the actual 0 point, some 19,000 feet to the northeast. Because of the bombing error, the blast program's effort to obtain basic blast data on a high-yield airburst was seriously affected. The free air measurements made by parachute-borne canisters were partially successful, since only low pressures were recorded at rather long horizontal ranges from the burst point, and the data could not be correlated with shock photography. Nevertheless, some basic data were obtained that will allow a limited evaluation of various scaling methods for correcting for the effects of atmospheric inhomogeneity. Analysis of these data is being made concurrently with similar information obtained by different methods on other events in the Redwing series. Another of the multi-megaton devices fired at Bikini was Navajo. 0 point was a barge in the lagoon off Dog Island. Studies were made here to obtain further data on water waves created by the energy release from high-yield devices. Such water waves are considered to be created by 2 phenomena. First, in the immediate area of the burst, energy transfer in the form of initial impulse and fluid displacement produce the most significant waves. Secondly, at more distant ranges, up to hundreds of miles, waves are initiated by an air coupling mechanism which is still being studied. Navajo was fired with a yield of 4.8 megatons. 17 minutes after the detonation, the water wave had traveled a distance of 18 miles, and this is what occurred on the island of Nan. Stop-motion photography recorded a wave some 11 feet in height as it swept across the island. On the island of Yvonne at Eniwetok Atoll, other blast studies were carried out. On a 40-kiloton surface burst, 10 jeeps were located facing into and broadside to the blast at distances ranging from 2,500 to 4,380 feet from 0 point. This and similar exposures on other shots were continuations of statistical studies from Upshot Knothole, Castle, and Teapot to assist in making damage prediction charts for TM-23-200 so as to provide added reliability for damage prediction to all types of military vehicles. Preliminary analysis of the data collected from jeeps indicates that a good correlation was achieved with the existing damage prediction charts for TM-23-200. Also on Yvonne, stations were set up to record drag force measurements on a 40-kiloton surface burst. Cubes, parallelepipeds, cylinders, and spheres were placed at 2,500 and 5,000 feet from ground zero and instrumented to check the correlation of field tests with wind tunnel and shock tube laboratory tests. Drag force data were obtained, which will allow comparison with the field results of Operation Teapot, and which can be correlated with identical scale models tested under laboratory conditions in the shock tube. Another objective of the blast and shock studies was to ascertain and investigate the existence of precursor waves resulting from surface firings, and to observe the difference in these effects over vegetated and sandy surfaces in a strong precursor region from a tower shot. The vegetation consisted of vines, grass, and broadleaf shrubs 10 to 15 feet high. In comparing findings from the cleared and uncleared areas, it was found that the vegetation had a suppressing effect on precursor formation and propagation as compared to that over a cleared area. It is believed that wet soil conditions and high thermal energy attenuation in the air of the Eniwetok Proving Ground adversely affected precursor formation, since precursors at the Eniwetok Proving Ground were weaker than those over the dry soil in the clear air of Nevada. Precursor-type waveforms were recorded on both surface events. In addition, a good range of crater data was obtained under a wide range of conditions and environments. For example, La Crosse was fired on the reef with a yield of 39.5 kilotons, and the crater was 404 feet in diameter, 44 feet deep, and had a 15-foot classical crater lip. Zuni was fired at Bikini on an island with a yield of 3.5 megatons. This crater had a diameter of 2,310 feet, was 103 feet deep, and had a 15-foot irregular crater lip. Such data will increase the reliability of crater predictions. The structures effort was chiefly concerned with checking the effect of the relatively long duration of the positive phase of the megaton blast wave on structural responses. During Teapot, the response to blasts of short-duration positive phase was studied. There were many unresolved questions concerning the applicability of a simplified mathematical model to the load duration problem. On Teapot, the responses of 4 typical single-story steel-frame industrial buildings to a 22-kiloton burst with a relatively short-duration positive blast phase were documented. The Redwing, or second part of this study, was made to record the responses of identical industrial buildings to a large yield detonation having a relatively long duration positive blast phase. An air burst with a predicted yield of 4.5 megatons was selected for this test. There were 6 steel frame buildings. The three drag-type structures were 30 feet high, 40 feet in span, and 40 feet long. The three semi-drag-type structures had the same height and span, but were 80 feet long. The 6 buildings were located on 3 man-made islands on the shallow water reef between the islands of Charlie and Dog and on the island of Dog, at ranges of 20,500, 24,000, 29,000, and 35,600 feet from the intended air zero, and placed so that the range and damage would be as great as possible. They were instrumented to obtain transient structural deflections, strains, and accelerations, as well as overpressure versus time and dynamic pressure versus time relationships. At shot time, high-speed remote cameras trained on the structures recorded arrival of the thermal radiation. It was also intended for the cameras to record arrival of the shock front, but they ceased operation prior to that time. Although the actual yield was only 3.8 megatons, the 19,000-foot bombing error to the northeast of intended Cherokee Zero caused all structures to be subjected to pressures higher than expected, and the planned gradation of damages was not achieved since all buildings collapsed. As a result, less data than expected was obtained on drag and semi-drag type buildings. Nevertheless, a comparison of the identical structures tested during Teapot and Redwing indicates that the most important result was a full qualitative demonstration of the greater effectiveness of the long-duration blast wave associated with megaton yield weapons. The thermal radiation and effects program had a primary objective of documenting the thermal phenomenology associated with a multi-megaton air burst. A secondary objective covered the collection of data on thermal phenomena and thermal effects on materials. The target miss on Cherokee seriously compromised the realization of the primary program objective, but additional data were recorded on thermal phenomena and thermal effects on materials. Studies of the effects of nuclear weapons on aircraft in flight, conducted previously during Operations Greenhouse, Ivy, Upshot Knothole, Castle, and Teapot, were continued. Previous tests indicated the critical importance of thermal effects on aircraft structures with respect to subsequent loading of the heated structure by both gust and overpressure. During Redwing, 6 Air Force aircraft, the B-47, B-52, B-66, B-57, F-84, and F-101, and 1 Navy aircraft, the A-3D-1, were primarily concerned with determination of delivery capabilities. Each plane carried a maximum amount of instrumentation, calorimeters, radiometers, and thermocouples for thermal input and response measurements. Transducers and strain gauges to record shear, bending, and torsion of the wing, tail, and fuselage surfaces. Other instrumentation included gyros to measure angles of roll and pitch, pressure transducers to record overpressures, accelerometers for measurement of structural accelerations, plus oscillographs and cameras to record aircraft positioning information, wing deflections, and other data. In the early morning before 0 hour, the effects aircraft took off from Eniwetok and headed for their shop time orbits. To position the aircraft at precise locations in space and to have a complete record of the flight paths at zero time and at time of shock arrival, various aircraft and ground electronic positioning systems were used. An important factor in the positioning of aircraft was the uncertainty of predictable yields for the experimental devices being fired. In general, gust response limits were set at 100% or less of limit load. Thermal effect responses were restricted to total temperature in thin skins of approximately 500 degrees Fahrenheit, and radiation dosage was limited to a 3.9 Roentgen total. Therefore, a positioning yield somewhat higher than the design yield was used in positioning the aircraft to provide a safety factor because of the unknowns of weapon performance. For example, with the Zuni device, the predicted yield was 1 to 3 megatons. The safety factor stated that aircraft positioning yield would be 5 megatons. The actual yield of this device was 3.5 megatons. Back on the ground following each mission, data reduction of aircraft effects began. The objectives of the aircraft effects program were fully met during this operation. A definite conservatism in the prediction methods for thermal inputs was noted, with predicted values being significantly higher than measured values. The results will be useful in developing more precise methods for prediction of thermal input and response parameters. Additionally, a conservatism was noted in the prediction methods of total dosage from nuclear radiation. Air crews received about half of the predicted doses. The importance of being able to predict radiation fields with resultant dosages to crews in the delivery of lower yield kiloton range weapons by high-speed fighter-type aircraft becomes paramount. As to blast effects, it was noted that the bomb bay doors and forward wheel well doors of the B-47 were moderately damaged at 0.84 psi on one shot. The B-52 bomb bay doors and various aerodynamic seals were damaged by both the thermal input and an overpressure of 0.87 psi on one shot. The B-47 and B-57 both sustained wrinkled control surfaces and tabs because of high thermal inputs. And the honeycomb skin of the F-101 was a thermal limiting item, with the skin on the stabilator and wing becoming unbonded with a temperature rise of about 450 degrees Fahrenheit. Such findings should be reflected in the design of future aircraft and the modification of existing models. During the Redwing missions, neither gust effects on engines nor overpressures and thermal effects on the various aircraft components created adverse control or performance problems. Delivery capabilities were proven out in all instances. Further testing of these aircraft to satisfy the Redwing objectives will be unnecessary. The biomedical effects program consisted of one project with the objective of obtaining information on the requirements for protection against chorioretinal burns. Rabbits and monkeys were exposed to the thermal pulse of several Redwing detonations. Timing and shutter mechanisms for fractionating the light pulse time-wise, and shutters and filters as possible protective devices for the eye were tested at all stations. The animals were exposed on 11 of the Redwing shots. And results indicate that climatic conditions and the thermal pulse characteristics at some exposure stations reduced the radiant exposure below the threshold necessary to produce chorioretinal burns. Both the first and second peak irradiances may produce chorioretinal burns, and the blink reflex is not fast enough to protect the eye. Data obtained should be of value in the development of eye protective devices. Another of the Redwing effect studies was concerned with the long-range detection of nuclear detonations by utilizing the electromagnetic pulse radiated by the detonation. This project had its major activity outside the Eniwetok Proving Ground. A network of distant stations from the eastern United States to Hawaii and the western Pacific were set up to detect the pulse from the detonations and study its characteristics. It was successfully demonstrated that operationally usable lines of position and fixes could be obtained from the bomb pulse at great distances. Distinguishing the bomb pulse from spherics, pulses from lightning and other natural sources still present some problems. Aerial photographic techniques were used to make photogrammetric determinations of various parameters of nuclear clouds as a function of time, and to attempt to establish approximate scaling yield relations. Excellent navigation, together with improved camera installations, made it possible to obtain more complete cloud survey data than on any previous operation. The nature and distribution of radioactive fallout from high-yield thermonuclear detonations was one of the prime objectives of the Redwing operation. It was an integrated program which included land, sea, and air stations to collect data during and after the fallout event. To measure the activity distribution within the nuclear mushroom, single-stage rockets were mounted and aimed to pass through both cloud and stem. The rockets, carrying detection units with telemetering transmitters, were fired into the stem and cloud at H+7 and H+15 minutes. The telemetered radiation exposure rate was then recorded on magnetic tapes in island and shipboard recording stations. To study the physical, chemical, and radiochemical nature of fallout after it reaches the surface, a number of collection techniques were used. Land stations located throughout the atoll consisted of total and time incremental collection devices for the purpose of gathering gross samples as well as samples versus time, from which time of arrival, rate of fallout, and time of cessation could be established. Since available land areas were covered by only a small fraction of the total fallout pattern, an array of floating instrument stations was moored within the lagoon and at sea to the north of the atoll. 3 pontoon rafts, instrumented to measure time of arrival, total exposure, and to collect total fallout samples, were moored in the lagoon. In addition, 2 YFNB barges with total and time incremental samplers and a variety of other instrumentation were moored inside the lagoon. In the ocean to the north of the atoll, some 16 skiffs were moored to collect total fallout samples, measure integrated exposure, time of arrival, and penetration of activity to various ocean depths. There were 3 fallout ships, YAG-39, YAG-40, and the LST-611, which were moved into position in the expected fallout zone prior to arrival of fallout to permit collection of total and incremental fallout samples at critical locations within the predicted pattern, as well as to make determinations of time of arrival, rate of arrival, cessation, particle size distribution with time, and other pertinent fallout parameters. The YAG-40 was outfitted with a special laboratory where early time studies of the collected fallout material were performed. Panels of typical building materials and common shipboard items were placed aboard the 3 ships for contamination-decontamination studies. In addition, masonite phantoms were exposed in a project to evaluate the performance of certain Navy dosimeters. The ships were also instrumented to measure the shielding effectiveness of various thicknesses of steel as a function of time, and to determine the gamma radiation fields produced by the ship's surface, air envelope, and water distribution of fallout contaminant, as well as serving to evaluate the effectiveness of washdown systems during fallout. The contaminated ships were utilized to test various decontamination procedures after their return to Eniwetok. To document the resulting fallout patterns, both aerial and sea surface surveys were carried out. P-2V aircraft, instrumented with very sensitive radiation detectors, were flown over the contaminated ocean areas to give an early definition of the pattern. This instrumentation was also used for making air absorption measurements, which permitted air survey data to be related to the exposure rates that existed 3 feet above the ocean surface. The surface surveys were accomplished by 2 destroyer escorts and the oceanographic survey vessel Horizon. Guided by the information resulting from the early aerial surveys, these ships moved into the ocean areas after fallout had been deposited to make exposure rate measurements just below the ocean surface. Periodic measurements of exposure rate versus depth, and to take water samples for analysis. This coordination of effort was made possible through the unified direction of the fallout program from a central control center. This Program 2 control center was located aboard the Joint Task Force flagship, the USS Estes. From here, communications were maintained with all elements of the fallout program. The YAGs and LST were positioned prior to fallout arrival based on predictions. The aircraft surveys were initiated and controlled, and the ocean surveys were directed, all under the supervision of the senior scientific personnel centrally located at the control center. In this way, an integrated effort of many separate elements was achieved, thereby resulting in a thorough documentation of the resultant patterns. To provide additional information on early cloud penetration and to permit determination of exposure and exposure rates encountered in flying through clouds produced by megaton range detonations, a number of B-57B aircraft equipped with appropriate instrumentation were flown through the stem and cloud base at times as early as 20 minutes after detonation. The data obtained is also valuable in determining the spatial distribution of the activity within the mushroom. During Redwing, all types of firings, air bursts, land surface bursts, and water surface bursts were documented to obtain the maximum amount of information on fallout phenomena. On all types, the concentration of activity in the stabilized cloud seemed to be more dense in the layers near the bottom of the cloud. The stem activity concentration appeared to be less than 3% of that in the cloud. The ocean and aerial surveys, in conjunction with the data from collector stations, permitted construction of fallout patterns from the contaminating shots. The Cherokee shot, intended as a megaton airburst over land, actually showed that an airburst over water does not produce downwind fallout areas of military significance. Whether or not this is the case over land remains to be determined. The land surface and water surface bursts did produce tremendous areas in which exposed personnel would receive lethal dosages. This data should be helpful in the construction of fallout models from which prediction methods could be developed. The data from Redwing confirmed the Castle finding of the significant extent of hazardous radioactive fallout resulting from the surface detonations of high-yield weapons. The results of the 8 weapons effects programs conducted during the 17-shot Redwing operation were many and covered a wide range of data. Because of the magnitude, it is possible to summarize only a few. The blast and shock program was successful in meeting its objectives, except for the loss of data on Cherokee. Aircraft effects tests proved out delivery capabilities in all instances, and Redwing objectives were fully accomplished. A comparison of the identical Redwing and teapot structures provided a full-scale qualitative demonstration of the effectiveness of the long-duration blast wave associated with megaton-yield weapons. The results confirmed on a full-scale basis theoretical studies which have indicated that as the length of the positive phase of the blast wave increases, the overpressure required to cause a given degree of damage decreases. The fallout studies of megaton-yield surface bursts during Redwing showed that the fallout hazard can be of military significance over areas of several thousand square miles. On all shots during Redwing, a high percentage of the instrumentation functioned properly and resulted in varying degrees of success in the documentation of megaton and kiloton effects. This documentation modified existing data, extended presently established theories, and added to the knowledge of phenomena in areas heretofore only partially documented.
This video was made possible through a grant from the Haas Corporation. The Geek Group would like to thank Haas for their continued support in helping encourage innovation in design and manufacturing in America. The Geek Group proudly features ISCAR tooling in all of our workshops, videos, and hackerspaces around the globe.
Hi there guys, I'm Chris Bowden.
And I'm ISCAR Rick.
Welcome to the Geek Group. Today we're going to give you a basic button tour for the Haas VF2. Now the buttons on your milling machine may be a little bit different, but the basic layout on Haas machines has been the same since pretty much the beginning of time.
Yep.
Yeah, and the buttons have evolved, the names and that have evolved, but the basic layout is pretty much the same. This is not a video to explain what every single individual button does. We will be doing that over the course of the series. This is the video so that when we mention a button in the future, you see something in a manual, this is the video you go to and say, where is that button? So because they're not all right here, there's some buttons around on the side, we're just going to cover the basics. So to get started, Mr. Rick, where do we, up here, this quadrant, okay, we've got reset, power up, restart, and recover. Now, we know the reset button, that does the thing. The power up, restart, use all the time. What's the recover?
Recover is if you have an alarm someplace and the tool changer's stuck in the middle of a tool change.
Okay.
With the recover button, it'll lead you through a ladder to fix your problem.
So these are the medium doom buttons and turning on and turning off. That's
right.
The big doom button is the big red one right here. This is a button we should talk about. This is the e-stop button. If everything goes sideways and the machine starts making really expensive sounds, the absolute first thing you probably want to do is just punch that. You don't have to be delicate with it. You don't have to be afraid of it. Slam that and everything instantly stops. It may make an angry sound doing it, but it's probably going to save you from doing something too terribly bad. When you come out of this, to turn this button off, you just turn it and then let go and then hit the reset and you'll clear out the error. All right, so the next quadrant of buttons is down here. These are our software buttons. They're just labeled F1 through
1 through F4. Yep.
Now these will change. These will do different things depending on what you're doing.
Exactly.
And then under here, we've got basic stuff for offsets, tool release, setting 0.
Yep.
So this
setting tools, setting offsets. That's a good setting
This
place.
is your setup area.
Yes.
So we've got tool offset measurement.
Yep.
Next tool.
Yep.
Now, this is different from ATC forward and ATC reverse.
That's correct.
This is, we're working on the next tool. This isn't changed to the next tool.
That's correct.
Okay. Tool release.
That's to release the tool. It's same as the button up on the spindle.
Okay. And they both work exactly the same.
Same. Yep.
Okay. Part 0
is
set.
setting your home position on your workpiece.
Okay, so just
your
setting
XYZ
offsets.
0. Yep.
Okay. That takes us into this quadrant. Now this will be different, especially the outside buttons. If you're on a lathe or a mill or whatnot, you'll see these change. And you may have buttons here for things that your machine doesn't have. If you, like this here, we've got the chip auger buttons. If you don't have the chip auger, those aren't going to do you any good.
The buttons will be there, but they won't do anything.
Okay. And we've got the coolant up and coolant down. If you don't have the adjustable coolant thing, that won't do anything.
Yep.
But here, this is our access control. So if you want to select Z, X, Y. The jog lock button's right in the middle,
Yep.
and that's got a couple different uses, but we'll get into that. And then we've got coolant down this side and chip stuff down this side. So this is forward and reverse on the conveyor and stop. And it's the same thing on the lathe.
Yes.
And then we've got the auxiliary coolant thing, and that's the little...
To put the coolant where you want it exactly.
Okay.
That's programmable.
So our next area here is the overrides. This handles all the feed rate. So it's -10, regular 100%, and +10. This is for tweaking on the fly.
Yep.
And then we've got hand control feed. So if instead of going up or down by 10, you can push this and then turn the knob.
And go up by 12%.
Yeah. Same thing here for spindles. So you've basically got speeds and feeds.
Yes.
Here. Down here, clockwise or counterclockwise, and then stop. This is spindle controls.
Yep.
So fast, forward and reverse. And then down here, basic rapid settings for 5, 25, 50, and 100%.
100% rapid overrides.
Okay. Up here, this is display. Take us through this. We've got programs conversions.
Right, this is for all your different programs, to find your programs. Positions.
Okay.
You have your work offset, you have distance to go, things like that. This is your offset page, all your different offsets, whether it be geometry, wear, height offsets, or your G50s.
Okay.
Current commands, this will tell you what the spindle RPM, this is just your information.
Okay.
All right. Your alarms and messages, if you have an alarm, it'll tell you what the alarm is, or a message left by somebody on the previous shift.
Okay.
If you left a message. Your parameters and your diagnostics. This is very rarely you get into this. This is usually for your Haas servicemen.
Okay.
There's not much you have to do there. Your settings, these are to personalize your machine for you. I want it to run in metric. I want it to run in English. I want all kinds of fun things you can set to personalize.
We're going to spend a lot of time in there.
Sure. Yep.
There's also another one about graph.
Graph, and that is you can actually in Graph you can run the program and watch it on the screen to make sure you don't have any issues where you need to hit the big red button.
So that's where you do all your simulations.
All your simulations.
And then we've got help and
calculator.
So there's a built-in
calculator and a help menu.
Okay.
Yep.
That takes us down into this quadrant. Mm-hmm. This is basic navigation. This is cursor navigation stuff. So home, end, which is go to the bottom, page up, page down, and then
and those will work in correspondence with your display.
Okay.
Yep.
So this gets you to the main area. This gets you to what
works
you're doing.
around inside that area.
Okay. Down here we have a basic keyboard. This is all of your letters, and then over here is all your numbers. The letters are not laid out in a QWERTY. It takes a little getting used to because it really is A, B, C, D, E. Yeah, it's the way they've done it forever. They leave it this way because if they were to go to a QWERTY, it'd screw all the guys up that have been doing it for a million years.
Right.
So this is a legacy type layout.
The story I heard originally, they did this because most of the machinists can't type.
Back in the day.
They hunt and peck.
Okay.
So they did it in alphabetical order for a lot of the guys that didn't use typewriters back
It makes
then.
sense.
And so they've left it since.
And we've also got an extra button down here, EOB.
End of block.
Okay. Over here, this is laid out just like a telephone.
Yep.
So, and then you've got your cancel space and right enter. This is
That's your enter
ends
button.
with this.
Yep.
Yeah. Now up here, the last quadrant, this is laid out kind of neat because this is all by line. So I'm going to go through each one by lines. What's our edit line?
Our edit line, we can insert a character, we can alter it, we can delete it, and Haas has a beautiful feature, it's called undo.
You use that a lot.
You use that a lot. They'll go, I believe, up to six entries.
Okay.
It'll undo up to 6 times.
Okay. The next one is memory functions.
Yep. Now you can run in single block, that's one line at a time. You can run it at dry run. This is for testing your programs. You have your optional stop, that'd be an M1.
Okay.
You turn that on, it'll stop. And then your block delete, if you have areas that you want to skip in the program, you turn this on and you can skip through it.
Okay.
Provided you highlighted it.
Now, what's MDI?
Manual data input.
DNC?
DNC is direct numerical control.
Okay. And we've got things like coolant, orient spindle, and then forward and reverse on
the automatic tool changer.
Okay.
Yep.
Next section is hand jog, and then we've just got numbers.
Right. The hand jog, this will operate at 1/10,000th of an inch. 1/1000th of an inch, 10,000ths of an inch, and 100,000ths.
Okay.
So every click would be in 1/1000ths. Every click it would move 1/1000th of an inch.
Okay.
Or every 1/10,000th, or every 10,000ths, or every 100.
Okay.
Okay.
The next one is zero return.
Zero return.
And then we've got all original, single, and
yes. And this is this zeroes out all your accesses at once. You can set origin. You can actually, if I want to do
so this is origin, not original.
Yeah.
This isn't like go to the original.
No,
this
is
is
an
set
origin.
and origin.
Yep.
Okay.
And then single, let's say I want to just send the X, the Y, or the Z. I say X single, and it'll send just that axis home.
Okay.
All right. And then you're home for your G28 for your tool change.
Okay.
Okay.
List programs. And we've got select programs.
You can send them, receive them. So if you're going to send them to your USB or through your cable, it can be send or receive or erase a program. So this is file sharing.
And on this particular machine, we have something that's relatively new. It's been out for a while, but a lot of people aren't really with it yet. This machine actually has Ethernet.
Yes.
So we get to teach all that. Something to remember while you're working in this quadrant is to get to anything in this row, you have to go through this button.
That highlights it and then makes this row active.
Okay. Now, are there, just out of curiosity, is there anything like where you don't do that? Like you'll be doing a thing in some operation and you just come over here and hit this, and you might be in the like hand jog, but the coolant button will do that, or anything like that.
If you're in hand jog and you're moving the stuff around, if you need to turn the coolant on, you need to highlight this and turn the coolant on.
Okay, so the only way to get here is through.
That's correct.
Okay. While we're talking about the fact that to get to these you have to go through these, that's true of some other things. There's certain things that require a button sequence.
Yes.
Okay. So just like where to get to anything in this row you have to go through this button to get there.
Yes.
There's some other things like the IPS where you have to go do a thing into another thing, and there's a system to it.
Yes.
Okay, and we'll talk about that in detail in the video for each specific thing. All right. We have to talk about the coolest control on here.
Yeah.
The big giant wheel of awesome.
Yeah, the wheel of awesome.
So this is a rotary encoder.
Yep.
It's a jog wheel is usually what's referred to in the manual. It's just a knob. It's numbered 0 to 100. And you use this for all kinds of stuff.
Yes.
This is, and it's not delicate. I've seen guys just, you just crank on this thing. You bang on it, and it's designed to take a beating, and you're not going to wear it out.
And you'll see machines out in the field from hanging on and going around a million times. It's actually polished from the skin. Oh yeah, yep. And there'll be a 1-inch diameter circle of polished, highly used
from the guy's fingertips.
From the guy's fingertips.
Okay.
Yep.
So that's the wheel of awesome.
Wheel of awesome.
Officially known as the jog wheel.
The jog wheel.
Okay. Now, some of the buttons on here are like 2-layer buttons. Explain that.
Explain by the settings in the graph.
Okay.
You get to the settings, it does all the settings for whether it be inch or metric or whatever you want to set. All right, the graph button will then bring up the page and you can do a program dry run and watch the program run.
So is this, you hit it once, you go to settings, you hit it a second time, you go to
That's
graphical
correct.
mode? Okay.
Yep, same with help or the calculator.
Okay.
It'll just bounce between the two.
Okay.
Yep. And your parameters and your diagnostics between the two.
Okay.
Yep.
Cool. So that's the main area buttons. Down here, the big green button.
That's your cycle start.
This is green means go.
Green means go. This is where you start making money.
Now, what's the difference between the feed hold here, this big red button, and this big red button?
This shuts the machine off. This shuts the hydraulics off.
Okay.
This just stops your operation where you're at.
But certain things are still going.
Yeah, the spindle's still running, the coolant's still on. It's just stop moving.
Okay.
That's all.
This is, and this is just, give me a second.
Hey, give me a second. Let me watch what you're doing.
Okay. And then up here, these are on
power
and
on
off.
That's it.
Now, over on the side, we have some more stuff. I'm going to turn this around so people can see it. Now, the top one is the USB port under its little protective cap. And I'll open this up. It's just a regular USB port like on the side of your computer. And we use this with thumb drives.
Yep, to load and unload programs.
And this is how we've put programs in the machine, like
unless
we're typing it in.
Yep.
So, yeah. Now, under that, we have a key switch.
Yep. We have 2 of them.
Yep. What are these for?
One of them is for program lock. You lock it out, you turn the switch, and then take this away. This way you can't edit a program.
Okay, so this is if the programmer and the operator are 2 different people,
yes,
the guy working third shift can't screw up the program.
Exactly.
Okay.
That protects it.
And the other one is just for
doing
setup on
the
machine so that you can do things with the doors open, stuff like that.
Right.
Down from there, we've got a couple blank spaces here. You may have these features. This is just different stuff. The one that we use here is, this particular one is for turning the lights inside on and off. This button is the reason why we're making this video, because for a lot of people, it can be tricky. It's like, where is the button to turn the lights on? That button turns the lights on and off. And it's the same button. You just push it, lights come on, lights go off. We need to take a minute and talk about the pendant. Now, this is one that you're not really used to because your machine doesn't have this. It's a remote control.
I know that.
It's pretty much entirely software buttons. You'll see that these aren't labeled. You've got basic cursor controls here. There's 2 different wheels. You've got the wheel here and the wheel here. This one is tensiony. Okay, so it
That's for moving feed rates.
Yep. And this, it will let you select different things. You can go
X,
through,
Y, Z, A, and
different
D.
axis, all kinds of stuff. And then it's got your awesome feature on top here with.
They had old guys. This
is new.
This is great. You know, old guys. You get that 40-something and you can't read. There you go. Nice job.
We've got another machine with a pendant, but it doesn't have this on it.
That's
also, you notice the pendant has a screen in that. It'll tell you, well, like right now, that's set for single would be this button, and option stop is here, and block delete is here. So, and then coolant over here. And then you've got your on and off. You can turn the machine on and off from here. So all the buttons on here are software controlled, so they'll change depending on what mode you're in, and the screen will change depending on what mode you're in. Like right now we're in MDI, distance to go.
Right.
So, and everything turns off when you put it back into thing. Now you're back to here.
This becomes control.
Yep.
When this is off, this is the control.
Yep. So that's pretty much all
all
the
the
basic
buttons.
controls. That's all the buttons. There are some other controls on the back, things like that. There's various valves and stuff, but that's pretty much only for the air system and that. And when we get into the details on the coolant system and the air system and stuff like that, we'll cover those specific controls. But those are pretty much set and forget buttons. Once your machine is installed and up and running, you're never really going to mess with that. So that's it.
Yep.
I'm Chris Bowden.
I'm Iskar Rick.
And as always, we'll see you next time.
The Geek Group would like to extend our deepest gratitude to the Gene Haas Foundation for making this program possible. Thanks to their generous contribution, we are able to train and inspire machinists all around the globe.
This video was made possible in part by Mastercam, whose CAD/CAM software provides the base to all code generated for Geek Group CNC projects. Operating the CNC machines in this video risks personal injury and mechanical damage. Hazards may include electricity, untrained operation, airborne toxins, flying debris and noise, fire and explosions, poor shop upkeep, sharp tooling, projectiles, loose clothing, inadequate clamping, automatic operation, automatic tool changer, unsupported bar, over-tightened steady rest, lack of enclosure, and impact.
This video was made possible by a grant from the Future Girl Foundation.
This video was made possible by thousands of private donations from members and viewers like you. Please visit thegeekgroup.org for more information on how you can donate and become a part of our dreams of Avalon.